Hello there! If you're watching this video, then I expect the puzzle on the screen is probably familiar to you. But if it isn't, and you're watching the video anyway, I'll quickly explain the rules. This is a sudoku puzzle, so the numbers 1 to 9 will appear once each in every row, every column, and in every 3x3 box. In addition to that, we have these 4 cages here. Each cage has a number in its corner that tells you the total of the 4 cells in the cage, and numbers are not allowed to repeat within a cage. And then finally, we have these arrows outside of the grid. Each arrow points to a diagonal run of cells like this, and the number on the arrow simply tells you the total. And unlike for the cages, these numbers are allowed to repeat. That's it, those are the rules. So what I'm going to do in this video is show you how to solve this puzzle, or at least how I intended it to be solved when I set it. Now, the easiest way to get started, and probably the only way to make any real progress at the beginning, is to consider these 4 cages, and in particular, to consider how they interact through the central region of the grid. We know this region has to contain every number 1 to 9 once each, that's just the rule of Sudoku. And so we'll start asking ourselves questions about where the various numbers can go in this box. These 6 cells in particular can never contain a 1 or a 2. If one of these cages contained a 2, then the largest sum we could make in 4 cells would be 2, 7, 8 and 9, which is 26. And if we had a 1, the largest we could make would be 25, and that's too small for these 3 cages, 27, 28 and 29. And so the 1 and the 2 in this central region have to go somewhere among these 3 cells. And we can say more than that. These 2 can't both be 1 and 2, because then we'd have a 1, 2 here. The largest we could make in the 25 would be 1, 2, 8 and 9. That's only 20. That's too small. So exactly one of these 2 is a 1 or a 2, and the final 1 or 2 gets pushed out into this cell here. And we'll just work our way up through the numbers doing the same thing. So where can a 3 go now? It can no longer go into 25, because we know it contains either a 1 or a 2. And if we had a 3 as well, the largest sum we could make would be 2, 3, 8 and 9. That's only 22. And a 3 isn't allowed in the 28 or 29 cages, because 3, 7, 8 and 9 is 27. And the only place left for a 3 is these 2 cells. So we've got a 27 cage, and we've got a 3 in it. That means we've got 24 to make in the remaining 3 cells, and that can only be done at 7 plus 8 plus 9. And so these cells have to be 3, 7, 8 and 9 in some order, with the 3 being in one of these 2. Let's keep going. Where can a 4 go? It can't go into 25 because 2, 4, 8 and 9 is only 23. It can't go into 29 because 4, 7, 8 and 9 is only 28. So the 4 must go in one of these 2. We've got 24 left. We have to use 7, 8 and 9. And so we get 4, 7, 8 and 9 in this 28. And exactly the same, I won't go through the details now, the 5 has to go in one of these 2, and the 29 cage is made up of 5, 7, 8 and 9. We've got one more interesting digit to consider, it's the 6. A 6 doesn't go into any of these cells because we've written down all of their possibilities and none of them are 6. So one of these 2 cells must be a 6. And now we can't have the 1 in these 2 cells anymore, because 1, 6, 8 and 9 is 24, which is just too small for this cage, 25. So we can't have a 1 here. These 2 cells become a 2, 6 pair. The 1 gets pushed out into the centre cell. And now we've got 8 in these 2, leaving 17 to make in these 2 cells. Well, that must be 8 plus 9. And so we've deduced exactly the contents of each of these cages. We just don't know exactly where the numbers go. But that's all right, we've made progress. So next we'll turn our attention to the next most restricted part of the grid, and that's these sums of 5 in the corners. There's only 2 ways to make a 5, it's either 1 plus 4 or it's 2 plus 3. So each of these cells is either a 1, a 2, a 3 or a 4. And there's a general observation we can make about the distribution as well, which is that as we go round the grid in order, 2 adjacent 5 sums can never be of the same type. What do I mean by that? I mean they can't both be 1, 4 and they can't both be 2, 3. Let's just see what happens. Let's say these were both 2 and 3. Well then, that would eliminate 2 and 3 from the rest of these columns. We've already used up all the 2s and 3s in these columns. They're in these cells here. And so in this box, we couldn't place a 2 or a 3 in any of these cells. We also can't place a 2 or a 3 in these cells because we already know those are 7, 8 or 9. And so we'd have to place both the 2 and the 3 in the one remaining cell, and that's no go. We can't put a 2 and a 3 in one cell. And so that's just a long-winded way of saying that as we go around the grid, these have to alternate 1, 4, 2, 3, 1, 4, 2, 3, or vice versa. We're not going to use that straight away, but it's good to keep it in your mind. So the next step, I'm going to highlight some cells in the grid. And if you're a consistent viewer of Cracking the Cryptic, then this pattern should be familiar to you. And there's an observation that has been made by a few people, but most recently and most popularly by Fell, and that was showcased in a Cracking the Cryptic video a few months ago, which is that the 16 green cells have to contain exactly the same 16 digits as the 16 blue cells. I'm not going to prove that fact to you. If you're interested, you can try and work out why, or maybe leave a comment and someone else will point you to the video that explains it for the first time. But the point is, the green cells and the blue cells have to contain exactly the same digits in some order. And that's interesting to us because in the green cells, we've got 8 cells that can only be 1, 2, 3, or 4. And in the blue cells, we've got 8 of them that can only be 7, 8, or 9. And so if these two sets are going to contain the same digits, well, the only way that that can possibly happen is if the green cells that don't yet have any 1s, 2s, 3s, and 4s in them contain 7, 8, and 9. And we've got to fit 8, 7s, 8s, and 9s in somewhere in the corners, and those are the only places where they can go. And similarly, we've got 8 1s, 2s, 3s, and 4s in the corners, which need to correspond to 8 1s, 2s, 3s, and 4s in the central ring, and we've only got 8 places where we can put them. So these cells have to be 1, 2, 3, or 4. And that's important because it lets us narrow down the possibilities for this 9 arrow. You see, in this box, the smallest that these two squares can now add to is 6. Why is it 6? Well, we've already got 3 squares in this box, which are either a 1, 2, 3, or 4. And so one of these squares has to be at least a 5. They can't both be less than 5, because then we'd have 5 squares, all of which were a 1, 2, 3, or a 4. There'd be a repeat somewhere. So one of these squares is at least a 5, and the other one is obviously at least a 1. 1's the smallest number. And so between them, these two cells add up to at least 6, which only leaves at most 3 in these two cells. So that means each of these two cells is either a 1 or a 2. And actually, this square can't be a 2 because of the 2, 6 pair we marked earlier, so this square is a 1. So now let's try and work out what happens along the rest of this diagonal. These squares can't both be equal, they can't both be 1. And the reason for that is by looking at what happens in the corners. If these squares were both 1, then that would eliminate a 1 from all of these squares. And that would mean that 1 plus 4 is no longer a possibility for these two 5s. They both have to be 2 plus 3. But we already said they can't both be 2 plus 3. They have to be of different types. And so this square is not equal to this square. They cannot both be 1s. And for exactly the same reason, these two squares have to contain different values. They can't both be 1s, and they can't both be 2s. And that means that actually this square can't be a 1. Because if this square were a 1, we'd eliminate 1 from both of these. That would make this 5 a 2 plus 3. We'd have to make 7 with these two cells. Now, given the 2 and 3 in the corner, the only way left to make 7 is 1 plus 6. And so one of these two cells would have to be a 1. But we've already said these two can't be equal. and these two can't be equal. But if we're going to put a 1 plus 6 in here, well, we'd have to have equal numbers either here or here. So that's an impossibility. This cell can't be a 1, and it has to be a 2. And now we've got 3 already on the 9 arrow. We've got 6 left to make in here. We already know one of these cells has to be at least a 5. We said that earlier. And so the only way we're going to make 6 here is if they are a 1 and a 5. Now this is a 1-5 pair, so we'll eliminate 1 from those cells. This 5 now has to be 2 plus 3, and this 2 here tells us which way round it goes. Now that we know this 5 is a 2 plus 3, we know the 2 5s next to it are 1 plus 4, and this 5 over here is 2 plus 3. And this one here tells us which way round this 1-4 pair goes. That's a 1, that's a 4. This 1 resolves the 1-5 pair. That's a 5, that's a 1, and that gives us the 1-4 pair over in this corner here. Let's clean up the pencil marks a little bit. This square must be a 4 now, because you can see a 2 and a 3. This square can see a 2, a 4, and one of these is a 3, so this one must be a 1. This is not a 1 or a 4. This square isn't a 1, and the 2-6 pair means it's not a 2. This square isn't a 2 or a 3. And the 1-4 here means we can eliminate 1-4 from those squares. Now, where in column 3 can we place a 2? It doesn't go here because of the 2-3 pair. We can see it doesn't go in any of those. It doesn't go in either of these because of the 2's over here. So this square must be a 2. And where in column 3 does a 3 go now? Well, it doesn't go down here because of the 2-3 pair. It doesn't go in these squares. It doesn't go in this square because of that 3. And it also doesn't go in this square because this 3 means that in box 2 there must be a 3 in one of these 3. Which means this can't be a 3, and the only place left is a 3 going there. That tells us which of these two squares is a 3. We already knew one of them was a 3. Well, it's not this one anymore. The 3 must go here. Here is where the solve really starts to get interesting. So let's get rid of our colouring. We're not going to need that anymore. Well, we're not going to need this colouring anymore. We are going to do some colouring. And what we're going to colour is the 7, 8s and 9s. We've got lots of pencil marks for 7, 8 and 9, but we don't know an awful lot about them, and we'd like to learn some more. And we're going to do that with the help of our colouring pencils. So let's use 3 colours, yellow, red and blue. We know that yellow, red and blue are going to correspond to 7, 8 and 9 in some order. We just don't know which order, but that's okay. We're going to try and work it out. So we know this 28 cage has all of 7, 8 and 9 in it, so it must contain each colour once. Well, this yellow square eliminates yellow from these 3, so this must be the yellow square in the 28. 29 also has to contain one of each colour. Well, the blue square doesn't go in one of these 2, so it goes in one of these. That means neither of these is blue, so this must be the blue square from the 28. Now, one of these is red. Whichever one it is, these 2 can't be red because they'll share a box with one of these. And this one can't be red because they share a row. So this must be the red square from 29. This yellow square now eliminates yellow from both of these, so this must be the yellow square from 29. And the blue sees this square here, so this must be the 29's blue square. Now that already lets us place another digit. Blue is either 7, 8 or 9, so it's not a 5. And the 5 on the 29 cage has to go here. And actually we can place a few more digits now just by normal sudoku. These ones and this one mean that the only place for a 1 in this box is here, and in fact we could have done that a while ago. We can place a digit here, and it's not a 1, it's not a 2, it's not a 3, it's not a 5, it's not a 6, and it's not a 7, 8 or 9 because this square can see a yellow and a red and a blue. So it must be a 4. And that lets us place a 4 here in this box because of these 4s here, which eliminate it from this square. And now this 2-6 pair gives us a 2-6 pair down here in this box. And finally for now, this 5 and this 5. Place a 5 here, this 3 and this 3 give us a 3 here. That makes this a 2, and this square must be a 3, because there's nowhere else a 3 can go in the box. Now we've done a good job already of colouring the 7s, 8s and 9s in the central area of the grid, but the key to carrying on with this all from here is going to be working out how to move those colours into the corners of the grid. Now, each corner box needs to contain a 7 and an 8 and a 9, that's just sudoku, that's the rule. And each corner box already has 2 squares that are either 7, 8 or 9, so there's got to be exactly one more in each box. And that leaves us fundamentally with only 2 configurations. If one of these is a 7, 8 or 9, then because of these 7s, 8s, 9s here, we can't have one here, so there must be one here. There isn't one here, so there must be one here. There isn't one here, so there must be one here. We've got this sort of windmill effect, and if we don't have one here, then the only other possibility is that we have one here, and then here, and then here, and then here. So we still have a windmill, just in the other direction. And that, it turns out, is the key to moving these colours into the corner boxes. So if one of these two is a 7, 8 or 9, then because of this domino down here, red and yellow domino, this must be blue. And if this is blue, then these two also have to be red and yellow, the same colour as this domino. And now we have one here, and because of this domino, this must be red, so these 2 squares must be yellow and blue, the same as this domino. We have a 7, 8 or 9 here, and that means these 2 have to be red and blue, and we also have a 7, 8 or 9 here, and that means these 2 corner squares have to be the same colours as this 8, 9 pair. We don't know what colour the 8, 9 pair is, but whatever it is, these 2 will end up being the same. And so this domino has shifted up into this box, this one has shifted down into this box, this one has shifted down into this box, and this one has shifted up into this box. And of course, if the windmill goes the other way around, then we still get the shifting, just in the other direction. This domino, instead of going into this box, comes down here, this one comes over here, this one comes up here, and this 8, 9 domino comes over into this corner. And so the point is, no matter which of the 2 options we're in, the colours of the pairs of cells in the corner boxes are exactly the same as the colours of these dominoes going around the outside of the central box, either rotated clockwise or rotated anti-clockwise. And it's that observation that's going to let us carry on with the next step of the puzzle. So this yellow-blue domino is going to come into one of these corner boxes, and the corner box anti-clockwise of it is going to have a red-blue pair, and the corner box that's clockwise of it is going to have a red-yellow pair. So let's suppose that the yellow-blue domino comes down here, and it comes in this order. Of course, we don't know it's going to come into this box, and we don't know which order the yellow and blue will be in, but it doesn't matter. I'm just doing this for illustrative purposes so you can see what will happen. We know its anti-clockwise neighbour is going to be a blue-red domino, and the blue here means that this one will be red. We know its clockwise neighbour will be a yellow-red domino, and the yellow square here means this one will be red. And so what we end up with is these red squares in opposite corner boxes, one of them on the outer rim of the puzzle, and one of them on the inside. And that's going to happen wherever we put this yellow-blue, and whichever order the yellow and the blue go in. I just put it here to illustrate the point that these red squares, one will be on the outer rim and one will be on the inside. And that means that we can never place a red in this corner box that's opposite the yellow-blue pair. So let's delete this for now, because we didn't know those colours were true. But the general point is that wherever this yellow-blue domino goes, whichever corner it goes into, the corner box opposite it is also going to be yellow and blue. And because the colours of the corner boxes correspond exactly to the colours of the dominoes, we know that this must be a yellow-blue domino. And so now we know that red must be 7. So we'll mark those as 7s, and we'll delete 7 from all the yellow and blue squares. Now we've got 8, 9 pairs that let us eliminate 8 and 9 from these squares. These become a 4, 7 pair. And what we'd like to do next is really narrow down the possibilities for where these 7s can go. Now remember earlier we said that wherever this yellow-blue pair comes, whether it goes to this corner or this corner, the 7s, the red squares, are going to go in the 2 corner boxes either side of it. And more than that, one of them will go on the outer rim of the puzzle and one of them will come into the inside. So the 7s either go here and here, or here and here, or here and here, or here and here. And some of those possibilities can immediately be seen not to be possible. For instance, this one I have highlighted now. If these were the 7s, there'd be nowhere to place a 7 in this bottom right corner box. This 7, and this 7 between them cover every empty square in this box. So these can't be 7s. In exactly the same way, the 7s can't go in these 2 squares, because that would leave nowhere for a 7 in this box up here. And that has given us a very useful 8-9 pair in the bottom row. That means that this square is no longer a 7, 8 or 9. It's got to be a 5 or a 6. And looking along the bottom row, this square is not a 7, 8 or 9 either. And so the 7 in the bottom row has to come in one of these 3 squares. And that has an important effect on this square. This square is not a 1, a 2, a 3 or a 4. It's not a 7 and it's not an 8 or a 9. So this square is also a 5 or a 6. And now finally we're going to make use of the 50 clue. These 3 squares always add up to 24 because there's one of each colour, 7, 8 and 9, that's 24. And these 2 squares are both at most 6. So that gives us a maximum of 12 from these 2 squares. Added to the 24 gives us a maximum of 36 from those 5 squares. So these 2 squares have to add up to at least 14. Well, this square here is at most 7, it can't be 8 or 9 because of this pair here. So this square has to be at least 7. It can't be 7 itself because of the 7 in the box, so it's got to be an 8 or a 9, and that makes it a blue square. It already sees a yellow. And now in this box, there's only one place left to put a 5, and that's here. We'll look at the other cell on the 50 arrow. It's either a 3, 6 or 7. Those are the only numbers missing from the row. Well, this square and this square have to add up to 14 at least. So there's no way this can be a 3. This square is also not a 3. And so the 3 in this row has to go here. And that lets us resolve the 2, 3 pair at the bottom of the grid. And that gives us the 2, 6 pair here. And also gives us a 2 over in this box. And now with the help of this new blue square, we can colour in most of the 7s, 8s and 9s across the whole grid. So this must be yellow, it's an 8 or 9 and it sees a blue. This must be blue. This needs to be red because it sees a yellow and a blue. This must be yellow. In this box, where can the yellow square go? It must go there. And we need this to be red, and this to be blue, this to be yellow, to be blue. And we've got a yellow here, so we can mark that as an 8 or a 9. And we can put both of these red squares as 7s and mark every blue and yellow square as either an 8 or a 9. Now by normal sudoku, this square isn't a 7 anymore, so it must be a 6. That puts a 7 over here. To complete this column, we need a 6. To complete this column, we need a 5. This isn't a 2 or a 3 anymore. We need a 7 here to complete the row. Let's make that red for completeness. And down here we have either a 5 or a 6. And now we're ready to make the final deduction about the 50 arrow. Now what have we got already? We've got 24 in these 3, we already know that. We've now got a 7 here, which I'll make red. So that gives us 31 from these 4 cells. These 2 squares here, well, they're either a 5 or a 6, but actually they both have to be the same. They're both the opposite of whatever this square is. So we've got 31 here. If these are both 6, that gives us 43, and we have to have a 7 here, which we can't have. So actually, these squares are both 5, and that puts a 6 here. That puts a 6 here. Now we have 5 plus 5, that's 10, plus 24, 34, plus 7, 41. This must be a 9, so we can go around the grid and make every single blue square a 9, and every single yellow square an 8. And now all the hard bits are over, it's just normal Sudoku to the end of the puzzle. So this must be an 8. Down here we're missing 1, 4 and 9, well the 9 must go here, 4, 1, this puts a 4 here. In this box that has to be a 4. Now we're missing 5 and 6 from the top row, 6, 5, 6. We've got 3, 5 and 7 to place here, that must go 7, 5, 3. That resolves our 4, 7 pair here. This 6 resolves our 2, 6 pair. 7 in the bottom row has to go here. We're missing 3 and 6 in that order. And now finally a 1 and a 2 over here, a 6 to complete the puzzle. And that's it. That's how you solve the puzzle.